Okay, welcome back. After a rather short break, let's start the last session of ESEM 2021 on mining software repository and energy consumption. We have two papers in this session. The first one will be presented by Vanessa Klotzmann in public software development during the pandemic. I'm Vanessa.
Hi, everyone. I'm Vanessa. In this first year of my PhD, in my first year of my PhD program, I conducted some software repository mining on determining was public software development activity during the pandemic, was it impacted in any sort of way? So let's get started. So today I'm going to give you kind of like a gist, like a summary of our work. So we're going to go through like a little bit of background information, the aims, the methodology, the findings from GitHub and Stack Overflow, the developer testimonials, and the conclusion. So as we all know, COVID-19 hit the world at a storm. Many companies had to adapt to new practices due to the pandemic. But also, as we all know, software development was always just like an activity that you could do no matter where you are around the world. But recent empirical studies document that COVID-19 might have had an impact on proprietary software development. So what are the aims of our study? So the big overview, the big picture of our study is, did the pandemic affect the developers' public contributions as seen on GitHub and Stack Overflow to major open source platforms? So the three research questions we're going to ask is, were there any sudden changes in activity coinciding with the global stay-at-home orders? Was public contributions in the year 2020 different from those between 2017 and 2019, and were the patterns of contributions disrupted in the year of 2020? So our methodology, we collected data from GitHub and Stack Overflow, from the GitHub archive dataset, and then from the Stack Exchange dump. If you're wondering why for Stack Overflow, we only collected data till November 2020, that was due to data availability. But in order to answer our research questions, we use a variety of different statistical techniques. We use ideas from outlier analysis, hypothesis testing, mean variance, and Shannon's entropy. So in order to answer our research questions, so for research question 1, we're using an outlier analysis. Research question 2, we're doing some hypothesis testing. And then research question 3, we are using a mean variance and entropy. So a few noteworthy terms for everyone to remember. As we're dealing with time series data, we have to check a few things. We have to check if the data is stationary or not. If the data is not stationary, we have to normalize the data. Normalizing the data is we're taking the difference between the consecutive data points, and that is called taking the delta. And to check if the data is not stationary or not, we can either do it by kind of like graphing the raw data points, or we can be doing do like a visual inspection of the graph, or we can compute an EDF test or KPSS test. So let's start with our little GitHub evaluation regarding our findings. So within our work, we looked at the different types of events GitHub has to offer, but we're going to present here the most noteworthy results, which are the push events. So let's answer research question number 1. Were there sudden changes in March and April 2020? If we look at the graph on the left-hand side of the screen, we see that in March and April of 2020, we have a sudden peak, a sudden change. So after checking if the data is stationary or not, we normalize the data, and then we get this linear regression plot on the right-hand side of the screen. And then we see March and April of 2020 ends up being an outlier, which is more than 3 times the standard deviation of the deltas. So now let's answer research question number 2. Was 2020 different from the recent past? It was not. there's no difference in the data distribution. As when we compared 2020 to 2017 and 2019, the data distribution is the same. And we can also see from this graph, there's nothing really that changes, except though for a few noteworthy outliers. So overall, the big picture, the yearly pattern of contributions regarding push events. Did we see a change? Yes and no. Yes, based on the number of outliers. As all of a sudden in 2020, we just had a peak in the amount of number of outliers. But we also did not see a change due to the difference of means is not statistically significant. And also too, we don't see a sudden really increase in the variance and entropy. So as I mentioned, we looked at the other events on GitHub. We looked at the events that were strongly correlated with push events. And the events that were strongly correlated with push events, we saw that they had those events had similar behavior to push events in respect to trying to answer the research questions we've defined. And the events that are not really correlated to push events, there's nothing really noteworthy about it, nothing really like interesting that like pops. So now let's look at Stack Overflow. So for Stack Overflow, we looked at different features. But what we present here today are the ratio of questions and answers. So were there sudden changes in March and April of 2020 regarding regarding the ratio of questions and answers in Stack Overflow? There was. On the figure on the left-hand side, it suggests that the year 2020 was different in respect to questions, to the ratio of questions and answers. People were asking more questions and answers. It is not included in the presentation, but if you read the paper, we talk about there's an increase in new users. So this leads to an assumption that maybe at the beginning of the COVID, people were making like new Stack Overflow accounts to ask more questions, though there was less contribution to answers. And we kind of see that there's a little bit of a peak here on the graph on the left-hand side of the screen. So after normalizing the data, because we saw that the data was not stationary, we end up with these two outlier points on the left-hand side, on the right-hand side of the screen. And we see like, okay, we get March and April is an outlier regarding to the ratio of questions and answers. And that kind of reflects to what we saw for new users and then also too for push events. But January and February is a little bit interesting, as maybe those are the activities that originated in China. But 2020, if we look at ratio of questions and answers, with respect to the comparing like the data to the recent past, it was different. And we can clearly see this from the graph that all of a sudden after January of 2020, the data just kind of like changes on the graph. We have different behavior. And finally, foremost, if we look at the pattern of contributions after in respect to ratios of question and answers for 2020, we see that the yearly pattern of contributions, we see that there's a big increase as the numbers have substantially got bigger. So the summary of, here's the summary of our results. So on top of doing some data analysis, we also took some developer testimonials. And we saw that there were mixed responses regarding if COVID-19 had an impact on software development or not. And our results are very similar to other works who did developer surveys regarding if COVID-19 like was a good thing or bad thing for their like work practices and software. And in conclusion, what we can see is that there was a noticeable different characteristics of 2020 event data, but unfortunately, we do have the threat to validity of bot activity, as maybe bot activity impacted our data. But that unfortunately is out of scope for our study. And for Stack Overflow, we saw an increase in new users and questions, and also to a large change in the ratio of questions and answers. And this could be, as how I mentioned before, the assumption that people were making accounts to ask more questions due to not being at work and needing to find a new kind of like way on how to get their questions solved as soon as possible. So thank you so much, everyone. And I hope you enjoyed a little glimpse of what we did. And I hope you read the paper and have a nice day.
Okay, thank you. Thanks, Vanessa. I really enjoyed the paper. I can say that. Let's see that there's no comments yet. Maybe they are coming. So while I was reading the paper, I got very curious, and maybe hopefully you can speculate a bit. Why do you think we got such a high ratio of unanswered questions during March, April 2020? So I know that you don't have an answer in the paper, but maybe you I really couldn't think about the reason why. So I'm curious if you have any intuitions or speculations about that.
Well, okay. So people, oh, I hear myself muted, like echoing. So basically, I think okay, that there was an increase in the amount of questions as obviously people need to figure out like, okay, how can I get this solved if like someone's not responding to me? But like, I think, and that affected the ratio of questions and answers. And I think that maybe the reason why people weren't answering is they kind of wanted their questions to be solved before answering someone else's question. But that's kind of hard. That was kind of a little bit, that was kind of something that was a little bit out of scope. And then also too, that we couldn't really figure out with the data available.
Yeah, one thing that I was just thinking is maybe one those questions, since many if many people were working, if those questions, maybe what was the quality of the questions of the unanswered one? Maybe it was also something to look into. If maybe there were, I don't know, there were many duplicates, there are many questions already solved somewhere, and people did not search Stack Overflow properly or something like that. I had the same curiosity also about the two outliers in August and December. I said, why is that? I have
no, of course. And then, but the thing though is unfortunately, when you're dealing with that data from GitHub, there's a lot of bot activity. So that's kind of, and that's mentioned in a lot of, that's, and that's out of scope of the study on how to filter bots out.
Okay, looks like your time is up. Thanks again, Vanessa. I really enjoyed reading your paper and the presentation. Thank you.
Thank you. Have a nice day. Thank you.
Yeah, thank you. So next presentation and the last one of the session and of ESEM is from Shaki Belgaid. Hopefully I didn't butcher your name. Apologies in case.
I'm Shaki Belgaid.
And the precise evaluating the impact of, no, sorry, this one. Yes, it's evaluating the impact of Java virtual machine on energy consumption. Right.
Hello there. We present you our work on the impact of Java virtual machines on energy consumption. Before we start, let's begin in some numbers. In 2013, more than 90 terawatt-hours of electricity has been consumed only by data centers, and this number has increased up to 140 in 2020. Another example of this huge consumption is the supercomputer Fugaku, who alone consumes around 30 kilowatts each year. Therefore, reducing the energy consumption of ICT became a major concern. We always want to optimize this energy on both levels, software and hardware. However, with modern architectures, it's kinda complex. And thanks to the distributed system and services, this task didn't become easier. So instead of trying to do it all by ourselves, let's focus on single brick. And this time, it would be the Java virtual machine layer. Before we begin in our study, we want first to describe the JVM. So basically, Java Virtual Machine or JVM is a middleman between the source code and the machine. Instead of trying to compile the code for every single operating system and machine, we will compile it only once and then let the JVM execute it in each operating system. Well, thanks to this approach, we can gather more insights of our code and its execution trace. Therefore, we can optimize the most repeated part of it in order to boost the performance of the program itself. And this is what we call just-in-time compilation, or JIT. Now that we understood our scope, let's try to answer those two research questions. The first research question will be about the impact of the JVM choice on the energy consumption. In other words, does changing the default Java virtual machine affects the energy consumption of the software? And the second one will be about how can we tune this JVM in order to reduce the energy consumption even more for those softwares. To answer the first question, we gathered more than 85 JVM candidates from more than 11 providers. And then we ran a set of benchmarks on them to see their energy behavior. Moreover, each benchmark has a purpose to test a different aspect of code. We used the most famous state-of-the-art benchmarks, which are Da Capo and Renaissance. And in this slide, we can see the focus or the target of each set of benchmark. As an example, we used Aurora for event queues, and we used ASL for more data-oriented works. Now let's discuss our results and findings. As we expected, different JVMs exhibited different behavior. However, as our surprise, there were some tendencies. Besides OpenG9 and GraalVM, who had their own unique behavior, most of the Java virtual machines followed the behavior of openJDK, especially after Java 11. The interesting part of Java 11 is that most of the JVMs have opted for the dynamic code evolution, which is an optimization on virtual machine that was first introduced by Terava distribution in Java 8. Hence, for further studies, we have considered to use four representative JVMs, which are OpenG9, GraalVM, openJDK 11, and openJDK 15. Example, if we zoom in openJDK as an example, we can see that each benchmark has its own optimal version, with special notice for reactors, who had suffered from some experimental features that were introduced in Java 11 and then got rolled back after the version 13. Now that we have covered the impact of the JVM choice on the energy consumption and found out that each distribution has its own spotlight, let's get deeper and study some configurations of those JVMs. In other words, can we tune the JVM in order to optimize even more this energy consumption? Was the most, despite the fact that OpenG9 was the most energy-hungry distribution in general case, as we have seen back in slide 15, OpenG9 exhibits a different behavior with the benchmark Aurora. Actually, it was by far the most optimal candidate. So we want to understand what are the reasons behind such behavior. So we have analyzed the execution trace of our candidates when they were running Aurora benchmark. And as we can see here, OpenG9 took only half time to finish the task. The main reason behind this is its number of parallel executions at the same time. While the number of active threads of openJDK and GraalVM was 2, G9 could raise this number up to 6, which is kinda surprising. The reason behind this is the different policy for memory allocation that was adopted by G9. G9 creates a non-collectible thread local heap within the main heap for each active thread, and the benefits for such cloning is a dedicated local heap for each independent thread, which means a faster access and no deadlocks. Just in time, further ado with the other experiments, let's start with the just-in-time compiler. Actually, we have been surprised that in 80% of the experiments, default JIT was the most optimal choice. However, for the garbage collector, the default one had only 60% success rate over all the cases. But when it succeeded, it saved up to 30% of the total energy consumption. In conclusion, to answer the second research question, we can say that most of the time, the default configuration was the optimal one, especially for the just-in-time compiler. To help developers and practitioners choosing an energy-efficient JVM distribution and configuration, we propose a tool named gReferral. Configurations Java application as an input. So this tool takes a Java application as an input and launch a script to tune the JVM configurations in order to choose the most suitable one among 85 JVM candidates and versions that were made available by SD Common. Beyond the JVM distribution and version recommendation, gReferral automatically explores many garbage collector and JIT options for each distribution. As an example, we tried to reduce the energy consumption of Z4G. So we used gReferral, and here he used more than 123 configuration between distributions and garbage collector and JIT options. And as we can see, the most energy efficient one was openJDK with Java 15. However, the most efficient one was actually GraalVM when we used the JVM-C compiler. JVM has its own. So, to summarize our work in a couple of words, we can say that JVM choice matters, and each JVM has its own spotlight and own weakness. Depends on the nature of the work. And the green one doesn't have to be always the most performant one, as we have seen in Zip4G example. Moreover, tuning your JVM can save some energy, but most of the case, the default configuration is a good candidate, and it will save you some time to not study those tunings. Thank you, and if you have any questions or insights, feel free to contact us.
Okay, thank you, Jackie. Thanks for the talk. If there are comments from the audience. Meanwhile, I have one. Actually, I would like to maybe talk a bit more about the extent of the impact on performance of when you optimize for consumption. So do you have an understanding about how much, can you quantify how much you can decrease the performance when you optimize for consumption? Maybe by JVM or in aggregate. I know there are many options and possibilities, but
yeah. So basically, for the calculate energy, it's basically the average power consumption by time. So most of the time, especially like with finite jobs, whenever we have the most performant algorithm tends to consume less energy due to performance or time interval. However, like for the server side, when we have like infinite time, sometimes it's worth to reduce the frequency of the CPU. And with this, we will reduce the average power consumption, which will impact, on one hand, the software or its performance. But on the other hand, it will save a lot of energy. So it's like a compromise between the CPU frequency and execution time.
Execution time. Okay. So, and what happens next with gReferral? Well, how do you plan on extending it?
Right now, actually, there are some good news about Java 17. They said it's more performant, more green, so we will include it there. And mostly what we are trying to do is collect a list of the most interesting configurations, and we put them in gReferral, so it will test them with other, more than what we have done with just the JIT and garbage collector.
So, but how does it work? I mean, you pick an application for reference, and then the gReferral execute the application using the JVM and the configuration. Is that what it does?
Actually, yeah, it's just like some statistical executions. Basically, it runs your Java code. So instead of running Java, your code, you just do gRefer your code, and then it will see its behavior among the different configurations.
Okay. Maybe, will it be easy to move it to the cloud? Maybe possible.
Yeah, well, actually now it's an open source project in GitHub, but to run it in the cloud, the problem is that, especially for energy consumption, the behavior of the program changes from one machine to another. So if you run it in the cloud, it might be.
So if it's elastic, the configuration on the cloud, it will completely ruin your data if things change. Okay, I understand that. Okay.
Yeah.
Okay, thank you. Interesting project. Thanks again. So that concludes our sessions for today. But just don't leave. After this, in 3 minutes, there is the closing and awards session. It's a plenary session that concludes ESEM. So I will see you there in a couple of minutes. You find the link, of course, again on the YouTube page of the ESEM conference, or just on the program on the conference ESEM conference website. Okay, thank you.